and the second one paired with the first one, delta JM.
Yeah.
So we can use identity over there. So your K is summed over. Your K is summed over. So now you can write EI delta IM, that means first one, delta second index, second one. That means forget about that K. We are dealing with the other two. So then IN JM, AJ, BM, CN. Now we know how to deal with this Kronecker delta. So when you have sum over one index, that's replaced. So you have delta JN AJ, that gives you AN. And you have BM, and that M is also summed with delta IM. So that gives you BI. And finally, you have CN minus, you have delta IN. So C is summed over that. So CI, then BM is summed over like delta JM. So that gives you BJ, and you have AJ. Right?
Yeah.
So now construct the full vector out of it. Construct the full vector out of it. So EI, BI, it gives you the full B vector, right? And ANCN, what does it give? What is ANCN, sum over N?
Dot.
Dot between what? A and C, right?
Yeah.
A dot C. Minus. So reconstruct the full vector like EI, CI, it gives you C vector. And AJ, BJ, what's that?
It's the dot product between.
So we got our result, right? This is we knew. So as you can see, using this Levi-Civita identities, Levi-Civita Kronecker delta identities, you can actually prove these vector identities really easily, and it's just double cross identity. So it wasn't that hard to prove in other way. But when you have more complicated identities, it'll come really handy. So practice on it and try to get expertise on it. It will be really useful. Okay, so I think we should take a break again. This time it will be 5 minutes break. Sorry, I'm lagging a lot behind.
Okay.
And this is the first day. But if you guys are following, then it's totally fine, because if I just be a little bit fastidious, if it is hard for you, then that's no gain, right? That's not a good way to do, good thing to do. Let's check who are with us now. So Ankon Dash. Okay, he left. Arafat.
Oh, yes, sir, I'm here.
Okay.
Sir, I'm here.
Yeah, I heard you. I heard you.
Yeah, I'm here.
Humaira.
Yes, I'm also here.
Jaber.
Yes, I'm here.
Juthi. Jaber, did you ask Maruf?
Yeah, I asked him. He's recording the class. If you need him, you can just give a message through work chat.
Okay. Pooja Bajaj, are you here?
Yeah, I'm here.
Are you following?
Yeah,
it's really relevant for you, right?
Sorry, what did you say?
I said it's really elementary for you. I mean,
No. Actually, it's been a long gap, so I forgot all those things, and I'm trying to recollect all those things. So maybe I can say it's quite difficult at this time.
okay.
Yeah.
Okay, Prashanto.
Yeah, I'm here.
Okay, Robin. Yeah, we are getting into more fun stuff. So, Robin. Okay, probably he's not here. Sifatul.
Yes.
Okay. Sulaiman.
Yeah.
Shubho.
Yeah, I'm here.
Okay, great. Okay, so we do not have only two people with us, like Alfred Havan and Love John.
So we have a break for 10 minutes?
Yeah, it is a break of 5 minutes. So we're already done in 2 minutes, so we have 3 minutes more.
Okay.
Okay, I think our break is over. I think we should start, right? Hello, can I start?
I think so. I don't know about that.
Okay, so let's talk about vector functions and scalar functions. So function, that means it has to depend on something. So typically it could be depend on space, it could depend on time. So first let's deal with the dependence on one parameter. So say you have a scalar function like temperature that is changing over time, temperature at a point. So rate of change of some scalar function f, that is a function of time, rate of change of that function with respect to time is defined as like this, right? We already know what does it mean and how we got that. So I'm not going to take it and just talk about it. I'm just write it down and go with it. So this is the definition of rate of change of f with respect to time, right? Respect to t. So f is a scalar function. It could represent anything, any physical quantity. And the very definition is like this. So Similarly, we can do for a vector as well. So for a vector, it's a little bit ambiguous. Ambiguous means we have to add, subtract with vectors. So addition, subtraction is not that simple with vectors like the scalars. So when we have a flat coordinate, like when we are talking about just one single point, then it's not a problem. We'll see that later why it's not a problem. When it can be a problem, we'll see that later. But let's not worry about that. So say at some point you have some vector at A. So vector A that changing over time. So A is a function of t. So at some time it is like that, sometime it's like that, or changing in magnitude like that. We define our derivative of A with respect to t in the similar fashion like we did with scalar fields, scalar quantities. We take like this. We evaluate that A vector at some future point like t plus delta t, a little bit future of that t point, then subtract A of t from that and divide it by t. So this subtraction between these two vectors is actually understood when easily understood when everything is happening at single point. Then it's not a problem, because at that point we have a vector space, and that vector space actually possesses both of those elements, like a at t plus delta t and A at t. So we can subtract that easily. So that's not a problem, but it will become a problem when we subtract two vectors that are not on same point. That means they possess in two different vector spaces. That's going to be a problem. Okay.
Wait, can you please repeat the last word? I didn't hear.
So I actually the whole differential geometry is all about that. So here we do not have a problem because our A, it lies in the same point. Say, actually for contrast, let's say we have a space.
In same vector space.
So here
You're talking about
at point x comma y, you have its own vector space at that point. Say you have an electric field vector over there. That electric field vector can change over time. So all electric vector at different times, they all belong to that point and that vector space. So then it's not a problem to subtract between a future electric field vector and the previous or past electric field vector. That's not a problem. But it's going to be a problem when you have two vector like two vectors, like at E at this point and another is like x prime y prime point.
Oh, okay. Yeah.
Then it's gonna be
discontinuity.
No, not discontinuity. Actually, we're talking about like it's distributed all over. So it's not the problem of discontinuity. The main problem is like they do not possess the same vector space. At this point, we have one vector space, and this point we have another vector space. We'll see why that later. Usually in elementary physics, we do not bother about that because in flat space, these vector space and that vector space, they actually coincide. So that's not a problem then. But when in curved space, they do not coincide, and then that's a problem.
Oh,
we have to deal with that. Okay, so it's a little bit complicated. We'll talk about that later. Let's not worry about too much at this point.
Okay.
Okay, so what happens when a particle actually follows a trajectory? So its movement is traced a long time. So say our particle under observation, it moves in 3 dimensions. Say we have a suppressed axis, so it moves along this line, and at some t, we have a position vector of that particular time of that mass point. We have this r. So this r is going to be changed over time, right? It'll trace out this line. This position vector will trace out this trajectory, right? as you can see in your imagination that it changes over time. So your R is now a function of time. So we can define several quantities, several useful quantities, that is derivative of this position vector. So one we define as velocity. So it's defined as like, actually the basic definition is written, so I just write this. So first order derivative of position vector of a particle is the velocity of that particle at that time. So at that time, that means this is gonna be a function of time as well. This whole thing is gonna be a function of time as well. So you have to written more explicitly like v as a function of t. Right?
Okay.
Yeah.
So if we use Cartesian coordinate, what happens? The representation of v we are trying to write is ddt of xi. X is x1 means just x coordinate, x2 means y, and x3 means z. Okay, so position vector can be written as xi ei, right, in Cartesian coordinate. Sum over I.
Yeah.
So in Cartesian coordinate, your ei, they do not change. They do not change over time or position or something. So derivative of that, it's not necessary. So that's zero simply. So we are left with this thing. So we can write it as like xi dot, by single dot we means time derivative. Sometimes we write it as like r dot. Okay. Also for the acceleration, it's defined as in the similar fashion. Acceleration is the rate of change of velocity, and that's also a function of time. So a of t is defined as dv of t over dt. So in Cartesian coordinate, we are lucky and we do not need to take derivative of ei. So we end up with having this. Agree?
Yeah.
Okay. So in Cartesian coordinate, we do not have a problem. But what happens in other coordinate, we'll see that in a moment. But before that, we need to prove a few identities. So a few identities regarding derivative. So let's prove it. So ddt of some vector a as a function of time and v vector as a function of time, you can prove it easily like it's dA over dt plus dB over dt. I believe you do not need any proof of that, right?
Yeah.
So if you have ddt of a dot b, then what happens? So the way you prove is you write a dot b as ai bi and use product rule that gives you ai dot bi plus ai bi dot, and in like it's the Cartesian representation I'm saying. So ai dot multiplied by bi is basically a vector dot with bi, a b vector, plus a vector dot with b dot.
Okay.
If you want a detailed calculation, you can do it. It's just that simple. Okay, so ddt of a cross b, what happens then? You can do the same way you did in the dot product, like you could write as ei epsilon I aj bj. Sorry, epsilon. Oops, actually, I'm looking into the clock so much, and actually I'm trying to hurry, but it gives you ei epsilon I jk aj dot bj plus ei epsilon ijk aj bk dot. So we can recollect again, and from this term we can see like it's basically cross product between a dot and b vector, plus this is just cross product between a vector and b dot vector, right?
Yeah.
Okay, so we are going to need that later. So now the most more interesting things. More interesting things. Oops. Let's clean up plain canvas. Okay. Now let's introduce a little bit different kind of coordinate. That coordinate moves along your particle. So in Cartesian coordinate representation, we saw like your particle moves like that, and your position vector, like you have a coordinate system here set up as a coordinate system. I'm suppressing the z coordinate, like z coordinate is out of the plane. So here we could actually, in principle, parameterize this particle trajectory and use that as our parameter for measuring velocity and acceleration, right? So that curve could itself be our coordinate system, could define our coordinate system.
TNB frame.
Yes, we are talking about TNB frame. Okay, so what is that? TNB, actually I should draw a space curve like that. That curve has a tangent every point on it, a normal vector to that, and binormal, that is normal to both t and n. This is t vector, this is n vector, and there is another vector that is normal to both, that is b. So that triplet that moves along this curve, so that we call TNB frame, because it's its initials like t, n, and b, like tangent, normal, and binormal. So that reference can be like used as like we can express our velocity and acceleration in terms of those directions in that frame. So that's what we are talking about, right? We can derive our acceleration and velocity vector in terms of those t and n, t and b frame, right?
Yeah.
Okay. So let's do that. Let's start with the velocity. Velocity is defined as v of t equals to dr over dt. So interesting parameterization we are doing here is that parameter actually the arc length of that curve as well. So how do we do that? So let's define that first. So if you have a small arc on that on that curve, on that trajectory, that has infinitesimal vector dr, norm of that dr vector is called ds, that infinitesimal length, right?
Yes.
Now at some initial point, if you starting from initial point up to some point, like if you integrate this thing, it gives you that s that measures the distance along this curve starting from that specific point, say O. Starting from O point up to some point, it gives you the total length, right?
Yeah.
And another interesting thing is that ds over dt, what does it represent?
Speed of the particle.
It's the norm of the vector. Why? Because vector itself is dr over dt. So if you take norm on both sides, dt is a scalar thing, so we do not have to bother about that. Then we are getting norm of dr over dt, which is ds over dt, right? So ds over dt is just the norm of the vector, we call it v. I mean, velocity vector, norm of the velocity vector, we call it v, the speed, right?
Yeah.
So what we can do is like dr over dt, we can, by chain rule, we can write it like ds over dt and then dr over ds, right?
Yeah.
Okay, so by definition, like by the definition of velocity, ds over dt is just the norm of the velocity v, and dr over ds is some vector that is tangent to this curve, right?
And it's a unit vector.
It's a unit vector as well. Yeah, we'll see that in a moment. So yeah, as he said, it's a unit vector. So let's see, it's a unit vector truly. So dr over ds, if you take norm of that thing, norm of the whole thing, it gives you norm of dr over ds, which is ds over ds, which is 1. So this thing is a unit vector. We can use it as a basis. We call it t vector, the tangent vector. This vector is tangent to the curve and has a unit magnitude, right?
Yeah.
So in TNB frame, in this new frame, our velocity vector, that v of function of t, it can always be written as magnitude of v and the tangential direction, which means velocity is always tangent to the curve that particle is moving on, moving through, right?
Yes.
Yeah.
Okay, so let's prove another interesting thing is that if you take derivative of that t with respect to s, that is normal to this t. Let's prove it. So we know that t dot t, as t is an unit vector, t dot t equals to 1. If we take derivative on both sides, we take
I will
dd
get
s. Sorry?
I will get 0.
You'll get 0, right? So if you use like the previous thing we proved that ddt of a dot b, we can write t dot t plus t dot t dot equals to 0, right? Dot product.
Yes, so they are orthogonal.
Yes, dot product is commutative. Oh, remember, I should not write it as dot. I should write it as prime because we are taking derivative with respect to s, not t. Okay, so dot product is commutative, so we can write it as like this thing. It means t and dt over ds, these two things are orthogonal, right?
Yeah.
Yeah.
Okay, great. So that means dt over ds, it must have a direction that is perpendicular to our tangent vector.
Yeah.
That specific direction, we call it as a normal direction. So we write dt over ds equals to some proportionality constant k multiplied by normal vector m. We can write that, right?
But still, it defines a plane. It defines a plane because
yeah, tn defines a plane. That's true.
no, just it's like wait. Any vector which is perpendicular to t defines a plane.
Yeah, that's true. Any vector which is not perpendicular to t should define a plane as well, because if you have the t this direction and you have another vector this direction, this angle is not 90 degrees, then you still have a plane, defining plane over there, right?
Yeah. Okay.
But this plane has a specific name. That's the point, right? You have a named plane on which the curve lies on. We call it the kissing plane or osculating plane.
Oscillating plane.
So there is a reason. We'll see that later. See that in a moment. Okay. So that proportionality constant k, we do not know its meaning now, but we'll know it later. Just hang on. So in terms of this new definition of t and n, we can write down our acceleration vector as well. See, so acceleration vector is by definition dv over dt, and we can again use chain rule and find like ds over dt and dv over ds, and we know what this thing is. We can write it as ds over dt multiplied by v dr over ds. Sorry, not dr over ds, it's just t. Yeah, like that. Oops, I forgot the DDS actually. Now it's fine, right?
Yeah.
So
yeah.
using product rule, we get ds over dt, dv over dt, ds into t plus ds over dt v dt over ds. Do you agree?
Yes.
Yeah.
Okay, great. So using chain rule backwards, we can write it as like dv over dt, right? And this ds over dt is just v, so we have a v squared. And this dt over ds is just k multiplied by the normal vector. So what is dv over dt? What is the dv over dt here? It measures how fast it is moving along the direction of velocity, right? So how fast the magnitude of velocity is
Changing.
increasing, right? dv over dt, increasing or changing, yeah. So rate of change of speed. This is some sort of acceleration, right? We call it a tangential acceleration because it lies along t direction. Plus, we have the rest of the thing, that is v square k multiplied by n. So from this point, it's clear that our acceleration, it totally lies on the Tn plane, and the velocity, it's just along t. That means the important quantities of motion, that velocity and acceleration, actually our Newton's law is enough, like Newton, if you know the initial position, initial velocity, and Newton's law defines that acceleration at that point, then you know everything about the motion. So basically your motion is confined to a two-dimensional plane, that is Tn plane. Instantaneously, yeah, along your motion that Tn plane is changing, but it's always the Tn plane that holds the motion, right?
Yeah.
That's why we call it an osculating plane. That trajectory of the particle, it kisses the Tn plane. It's known as the kissing plane as well. Okay. Next, what's the interpretation of this k? So let's do the math for circular motion. If our particle was moving on a circle of radius r that is not changing, then this r is related to the s, is like if it creates an angle theta, sorry, d phi inside, then this arc is related like this, like ds equals to r d phi, right? R is a
Yeah.
constant. I should write capital R here. So V, this thing is like R d phi over dt. So what's this quantity?
Angular velocity.
Actually, did I made a mistake? No, I did not. Magnitude of velocity is this, right?
Yeah.
Yeah. So d phi over dt, what's that?
Angular
It measures how fast the angle is changing, the inner angle. So that is r omega.
Yeah.
Okay. Then what's the acceleration? So this thing lies along the t direction, right? So acceleration A would be ddt of vt, that v is not changing because omega is a fixed quantity, r is a fixed quantity. By our definition, it's moving on a circle. So this thing is not changing. The only changing thing is this thing. So we have like v multiplied by dt over small dt, which is we can introduce the same parameter. That means v ds over dt, dt over ds, like that, and have v square, and then what's this part? It's k times n.
Yeah.
N is the normal to the unit normal to the t vector, right?
Yeah.
So our a, norm of a vector is this. So norm of a is what? It's v square k.
Also, it's 1 by r in that case.
Yes. Yes. So
It's
our
radius.
k is 1 over r, right?
And also, n is toward the center.
Yes. N is towards the center, right? N is this direction. Do you need explanation with this, like why it is k equals to 1 over r? We can do a little bit more math into it. Like we can do it. It's simple. We just need to do a like calculate everything in polar form and find this thing. Okay, let's do it. Let's do it. It's simple. So if it is moving on a circle that that has a radius big R, this thing, then coordinate at this point x equals to r. If this angle is phi, then r cosine phi, and y equals to r sine phi, right?
Yeah.
Yeah.
So position vector, rate of change of position. Rate of change of position vector dr over dt is ddt of r cosine phi x hat or e1. I would write. Can I write x hat? It's convenient for me. Can I write x hat? X hat is this direction, and y hat is this direction. So r sine phi y hat, and if you take derivative with respect to that, it gives you you just have your r out of this derivative, so r, and by differentiation you have what? ddt of not ddt, like you have d phi over dt and then minus sine phi x hat plus cosine phi y hat. Do you agree with that?
Yeah.
Then take the second order derivative. So this is your omega. This is d phi over dt. I consider this as constant. So this is your omega. So dr over dt is this thing. Now if you take another derivative, it gives you d2r over dt squared. Here you have your r that remains there, but that omega also remains there. But when you take derivative with respect to that, you have a variable phi inside of it. So you have d phi over dt again. So that gives you omega squared. And you're left with negative cosine phi x hat plus sine phi y hat. Right?
Maybe the plus will be minus sign.
That should be minus, yeah. So it's basically, we have that r omega squared negative of, what is this direction? Like cosine phi x hat plus sine phi y hat. Cosine phi x hat plus sine phi y hat is this direction. So it's just negative r hat direction, right?
Yeah.
Now, if we include our v inside of this expression, r omega square is how much? Like v equals to r omega. So we multiply by r and divide by r, right? So r square omega square is just v squared divided by r, and this is negative r hat. It's a unit vector, which is we have been seeking, that is n vector, right? So for this specific case, n vector is negative r hat, and we can see that for in our definition that k equals to 1 over r. Just match these two things. Right? So we can replace that for a general case. We can replace that thing by this. What this r is, it means if you have a particle moving, okay, actually it got messier. So let's do it here. So we got that our acceleration a, it resolves like this, at t direction, actually it resolves like this, dv over dt, or more generally I can write it as s double dot, right?
Yeah.
And then t plus v square k n. Now by comparing with this one, we can write it as v square over k, v square over r, like that. So our motion that that takes along this TNB frame, and this r is actually a curvature radius of that local circle that we can draw. Like if we take a small piece of it and find the whole circle, that whole circle will have a radius of r. So it can change over time. No, radius of curvature is k. Radius of curvature. Yeah, it's the radius of curvature. Yeah, it's the radius of curvature. What's the definition? Yeah. Curvature is k. Curvature is k. Yeah, the radius of curvature is r.
Why kappa is actually the curvature. We can prove it by drawing this local circle from the definition dt by ds by considering a little change of the motion of the particle.
Yeah, you can do that as well. Okay, so we got our, we sometimes call it as a resolute of acceleration. So we have resolved our acceleration in two parts, that is tangential part and another is normal part. right? And for velocity, we have s dot t. We can
so
find
there is
another
no confirmation
normal
of the B vector in the in this kind of mode.
The definition of B vector is like this: T cross n. It defined as like this.
Okay.
It's binormal. Like it's defined such a way that it's unit and it's also perpendicular to the both.
Thank you.
Okay. So question is, how do we use that? So right now we do not use that at this moment. We are not at that level that to use this result, but we can talk something about it. Like here, our unit vectors, those are not constants, right? This t and n, these are also functions.
Yeah.
Those are function of time, you could say. Those are function of Arctic parameter, you could say. Yeah, you could write in both ways. So in principle, it's not necessary that our basis vector, those are constants. So for Cartesian coordinate, it's a real spatial coordinate in this way that the basis vector, like the unit basis vectors in Cartesian coordinate, that x hat, y hat, and z hat, those are not dependent on either space or time. Neither it's not dependent. So whenever we take differentiation, it becomes 0. So that's a really special quality or property of Cartesian coordinate. So what happens if we move into polar coordinates, particularly cylindrical polar or spherical polar? So can we resolve our acceleration there, like in the similar manner? Here it's not any specific like cylindrical or polar coordinates. It's an intrinsic coordinate that intrinsic to the specific trajectory. So physics wise it might be useful but for problem solving you need a specific coordinate. You do not need an abstract one like this. So instead of using Cartesian coordinate, obviously you could use polar coordinate, cylindrical polar or spherical polar. So we have two definitions for cylindrical and polar, spherical. Cylindrical polar coordinates and spherical polar coordinates. Okay, cylindrical polar coordinates is measured like this. To reach any point, any particular point, okay, in 3 dimension. Okay, let's draw it later. Let's draw it later. Say we have a 3-dimensional system and we are trying to reach this point that is labeled as x, comma y, comma z. So first we go on the xy plane. We take a projection of that point on that xy plane, probably leads us here. So this distance, it's labeled as rho, and the angle it creates between the x-axis and y-axis, that means this is our x-axis, so we need the other one. This thing, this called phi, and the height we travel along here, it's the z. So the relation between Cartesian and polar, spherical, cylindrical polar, it's pretty simple because z coordinate remains the same. X coordinate is just this rho is the radial distance, like radius of the cylinder, hypothetical cylinder that particle lies on. Rho cosine phi, and y equals to rho sine phi, right? So why we call it cylindrical coordinate? Because we assume there is an hypothetical cylinder of radius rho on which actually that particle lies. So we use that coordinates drawn on the cylinder to distinguish that particle, that point. Similarly, for spherical polar coordinate, we actually do it a little bit differently. This is the point, so we call it a radius r. This is the distance, and then second angle, how much that thing creates an angle with the z-axis, and then we take the projection on the xy plane of that thing and say how much that thing creates an angle with x-axis. So these three levels are the polar coordinates. So relation between Cartesian and spherical polar is like this: x equals to r sine theta cosine phi, y equals to r sine theta sine phi, and z equals to r cosine theta, like this. So it's called spherical polar coordinate because we are using here a hypothetical sphere on which that theta phi coordinates are drawn on, right? So what about we use this level and like try to resolve our polar coordinate and all that? How about using these? So we know there are many good behavior of Cartesian coordinates. So we start by writing our position vector in terms of Cartesian coordinate, that is x hat plus y hat plus z hat. Then to transform it into cylindrical coordinate, we just plug in this expression over there. So it gives us rho cosine phi x hat plus rho sine phi y hat plus z hat. This is our r. Then we take derivative to find velocity. We take derivative with respect to t.
There is a y hat missing, rho sine phi.
Yeah. Thank you. So if we take derivative with respect to t, we have to use product rule, right? So it gives us rho dot cosine phi plus rho phi dot cosine sine minus, actually it should be minus, right? Taking derivative.
Why are not we changing the basis vector?
Sorry?
Why are not we changing the basis vector?
How do we change basis vector directly?
Okay, we can write r from.
Yeah, you can write it like this thing. These two things you can combine, and you can using that definition and find like that. It's basically this, right?
Yeah.
Problem is you do not know how to take derivative of rho hat. That's the problem. So that's why
we can derive and we have learned it.
Yeah, that you can do, obviously. That you can do.
Okay.
But for Cartesian coordinate, you do not have to be that much careful while taking derivative of that x hat, y hat, and z hat. So that's the advantage. This rho hat, it's changing over point, right? Every point. Okay, so this is x hat plus then how much is y hat? It's rho dot sine phi plus rho phi dot cosine phi y hat plus z hat, z dot z hat, right? So now we can actually separate that rho dot part and phi dot part. So if we factor out rho dot, we get cosine phi x hat plus sine phi y hat plus rho phi dot negative sine phi x hat plus cosine phi y hat plus z dot z hat, right? Now we can argue that this part is actually a unit vector. You can take dot product with itself, and you can say that okay, it's unit vector, and we can assign a name to it. We call it a row hat. So this is how we usually do. Then we have row phi dot. Then this vector negative sine phi x hat plus cosine phi y hat. You can convince yourself that it's also has a magnitude of 1 because sine square phi plus cosine square phi equals to 1, and it's also perpendicular to that vector. Take dot product with that one, you'll get 0. So we call it a new thing. We call it because when phi dot is changing, we have that specific direction. So we call it phi hat. So rho hat and phi hat both are unit normal vectors, but rho hat tells the direction which in which direction that rho changes, and phi hat tells the direction in which phi changes, right? So this is our V written in cylindrical polar form. We can call our rho dot as V rho, and rho phi dot as V phi, and Z dot as VZ. Right?
Yeah.
Okay. So similarly, we can again take dot derivative of V to get acceleration. So A equals to dv over dt, and now your rho hat and phi hat are actually changing, so you have to take care of that as well. So dv over dt, that gives you rho double dot rho hat plus rho dot rho hat dot. So we are not going to do rho hat dot directly because that's we have to do a side calculation. So we actually substitute that thing directly, like we have a definition of that. So ddt of cosine phi x hat plus sine phi y hat, this thing, right? Plus then we have rho dot phi hat. Did I make a mistake? No, I did not. Plus rho phi double dot phi hat plus rho phi dot phi hat dot, but instead of doing that, like writing that way, we just substitute directly over there ddt of minus sine phi x hat plus cosine phi y hat, and then plus z double dot z hat. Are you okay with that?
Yeah.
Okay, now if we take differentiation, then we already had rho double dot rho hat, that's fine. Then rho dot, and if you take differentiation of with respect to t, what do you get? You have a phi dot as well, right?
Yeah.
And you get negative cosine, negative sine phi plus cosine phi, like that.
It's phi hat.
It's phi hat, right? It's phi hat. Plus, yeah, write these three terms down. So rho dot phi hat plus rho phi double dot phi hat, that's fine as well. Then this part, how about that? So you have rho, you have phi dot, then when you take differentiation of that thing, you get a phi dot again, right? Because it's a function of phi. So you get phi dot squared. Also, you have minus sine phi, cosine phi x hat minus sine phi y hat. What's that?
Minus rho hat.
Minus rho.
That gives you minus rho hat, right? So you have minus rho hat plus z double dot z hat. So you got your cylindrical polar resolute of acceleration, that is rho double dot, then where is rho hat again, minus rho phi dot squared rho hat, right? Plus 2 rho dot phi dot plus rho phi double dot phi hat plus z double dot z hat. You can call this thing as your a rho. You can call this part as your a phi and this part as az. So what does it mean? This part a rho is the acceleration along the radial direction. So how much it wants to go out of that cylinder, like how much it tries to increase its radius. So if you have your rho double dot, then it's positive, but the much you have your angular velocity, it reduces, right? The tendency. So when you have more tendency to rotate, then it has like a less tendency to go out of that cylinder, right?
Yeah.
Okay, so the next part is phi hat. So phi hat already has a angular acceleration term, that is I shouldn't call it angular I call it angular acceleration, right? It's angular acceleration. So phi double dot is angular acceleration. So you have an angular acceleration term, and that's obvious that it should be along the direction of phi hat. That's okay. But what about this term? It's a combination of rho dot and phi dot. So those are velocities. Rho dot is a velocity along rho direction, right? And phi dot is a velocity along phi direction. So it's a product of the thing.
Coriolis effect.
No. Don't confuse with non-inertial frames. You are doing inertial terms. These are all inertial things. You are just resolving your acceleration into different coordinate. That's it. It just looks different, but this is the same acceleration. There is no like Coriolis or like centrifugal terms here. It's just your velocity contributes to your acceleration. That's the thing. Because of your changing of your basis vector as well. That's an effect of effect that your basis vector changes along along your movement, along your trajectory. So you can think of like that. Actually, you are changing your measurement. That's the thing, the right thing to say. Let me explain what really happening here. So say at this point you were saying that your phi hat direction is upward. Now after a moment you are saying no, my phi hat direction is this way. So you are actually changing your unit basis, unit vectors. So that's why we have this these terms. If you are you have changed your representation of acceleration, that's all. It's not non-inertial terms. Any question regarding this? I think
well, if we compare these equations with our TNB equations, we see that Fi is in the direction of tangent. So, but the other tools, from the other tools, the rho hat is in the opposite direction of n. So what does explain the AZ, the B?
No. That's basically your definition of n. Like our n direction is like negative rho hat here.
Yeah.
Right?
Yeah.
And those are two different coordinates. Do not compare that.
Okay.
They might have some similarities, but they're two different things. Why? Because one of their origin is here actually, and in this coordinate our origin is here.
Yeah.
In that thing, we have been measuring our like initial point from here and measuring along this. Here we are not doing that.
Okay.
So these are basically the effect of changing of your basis vectors. That's I can say. So your rho hat dot, it gives rise to something. Also your phi hat dot, it gives rise to something. So you have to take into account that thing as well, that your representation along your time, your representation has changed a little bit. Actually, in GR, we'll find these terms as gamma terms. We'll call it connection coefficients. We'll see that later. Probably 10 to 12 lecture. Okay. So this is the cylindrical representation. What about spherical polar representation of acceleration? Can you do that? Here, can you start?
We can.
Can you start this thing and derive that?
Yeah, we can. If you want, you can just write the result.
I do not have, like, if I have to write it, then I have to derive it. I do not have it.
Okay, so actually we can, I think.
So you just search on the internet, like polar acceleration, spherical polar representation of acceleration, you'll find the result. You can derive it. It's pretty simple. It's just substitute similar manner, like you have your r, then take velocity, like first order derivative, then second order derivative, and combine those terms. Just remember, when you have like this kind of term, like delta r over delta r, we call it r hat. In general, actually, we call like this. Some unit basis vector ei is defined as like delta r over delta that specific coordinate normalized to that one, like 1 over delta r over delta xi norm of that. Just remember that. So if you have like your e phi in this thing, you have like 1 over delta norm of delta r over delta phi and delta r over delta phi, like that. So such a way that those are unit. Okay. I think you can derive that. That's pretty simple. That's you have to do some more algebra. That's true, but it's not that complicated. Okay. I think I need a break. Five minutes. Hello.
Yeah.
Hi, can you start now?
Yeah, I think.
Okay.
Fine.
So how?
Is this the final session?
Yes, this final portion. Yeah, we are lagging behind a lot.
Yeah, I think it is almost impossible to cover all the topics.
Yeah, it happens every year. It doesn't matter. At the end, we'll catch up, because the later the chapters are actually more like I have kept more like comfortable schedule at the later time, so we'll catch up. Okay, so we all know about Newton's laws, right? Newton's law, the first law says like a body remains at rest or in uniform motion unless acted upon by a force. So as long as you do not give a force to an object, it remains uniform motion. It remains on a uniform motion or in rest, right? We all know that. Question is, how do you know it's in uniform motion? I mean, how can tell that something is going on a uniform motion or moving on a straight line? What do we mean by a straight line? Like in polar coordinates, say we have like this, we have drawn like this. This is our phi axis, this is our r axis. If something moves like this way, this vertical direction, is it moving?
No.
Moving in? Is it in a uniform motion? No.
No.
It might look straight, but
it is moving in circular direction, I think.
It's actually orbiting, right? When we are drawing like this. Okay, so how do we know that it's in uniform motion? So then it comes the $1 million question, that what is this thing here, d square here? So for the moment, let's do not worry about other coordinates. Let's worry only about Cartesian coordinate and in Euclidean space, because like we'll see this kind of thing later. It's not clear enough here that why it is not a straight line, or this is not a uniform motion, because as long as you do not have a definition of d square, you cannot tell. Okay. Actually, you can tell, but at least something has to be defined on that. So we'll see that thing, this we call it covariant derivative, that has to be defined. Like connection coefficient has to be defined on the system. Otherwise, we cannot tell if it is a straight, like it's uniform motion or not. We'll see that later. So at the heart of Newtonian mechanics, there are some ambiguities at the fundamental level. So that are resolved in GR. So that's our main goal. So let's review our Newton's law and motion in non-inertial reference frame for now. Then we'll learn in detail later. Okay, so the second law says a body acted upon by a force moves in such a manner that the time rate of change of momentum equals to the force. Because equals to, I mean, this tells us that F equals to ma, right? This is basically our old
dp by dt.
Yeah, dp by dt. F equal ma. Because our definition of acceleration, momentum p, is this when this thing is a constant. Why? Because we are talking about point particles. So that's why it reduced down to F equal ma. We'll generalize these ideas. But interestingly, when we are done generalizing things, in 4 dimension even, we'll restore this formula again. F equal ma will remain invariant. Like it'll become a 4-dimensional version of this, but okay. And the third law says, like, if two bodies exert forces on each other, these forces are equal in magnitude and opposite in direction. It actually defines a like practical way to measure forces. So when we have an isolated system, we have two objects acting upon each other. So we know if someone is giving a force F1 and another is giving a force F2 on another, so we know that F1 plus F2, it has to balance, right? So if we know nature of one thing, in terms of that, we can immediately recognize the other thing as number one as a force and how to measure that as well. So that's basically what Newton's law says. I'm not going into deeper thing. There are many thought of school that debate about which one is law, which one is definition, but we are not going into that. The thing we are interested in is the motion in non-inertial frames. What happens when we are not in an inertial reference frame? So that's the biggest question. So here, when we say F equal ma, we are actually in an inertial frame, right? When our A is defined as like this thing, d2r over dt squared. Right? Hello?
Yeah.
So we are all happy with that, right? We are already happy with our old friend Newton's law.
Yeah.
We can move from here. Okay. So how two things can, like two coordinate frame can be related? Two moving coordinate frame can be related. So let's say we have one coordinate system, that is, we call it primed coordinate system, that is stationary. Call it S prime. So its coordinates are x1 prime, x2 prime, and x3 prime. And this one is stationary, and another is, like, this is an inertial frame, and another is not. So this is x1, x2, and x3, and this is S frame. So they measure same event, same particle. They talk about same particle. So position of a particle from the perspective of S frame is this thing, and he calls it R vector. And the uniform motion one, he calls it R prime vector. And their origin is separated by this. Then by vector addition law, we have our R prime vector. That means the position coordinate of that particle P seen by the like measured by the uniformly moving observer, inertial observer, that is R prime, equals to R vector. That means there's separation in between those plus R.
Yeah.
Now, apart from this movement, they have one extra motion, that is, this one can be rotate. This can be rotating. So basically, when you have two rigid systems, because when we assume two frames, one is inertial, another is non-inertial, probably one is rotating with respect to other, then in principle we have 6 degrees of freedom with in the system, because in terms of this, in like seen by this inertial observer, the second one, its origin can have like 3 coordinates like x, y, z, That's why we have 3 degrees of freedom here. And also, it can rotate in 3 different ways. We know these as Euler angles. So that's 3 more degrees of freedom. So we have 6 degrees of freedom in total here. So we have to isolate those and extract its physics from there. Yes. Okay, so first consider a very specific situation when their origin is coincident. That means r equals to 0 in that situation. A very special case. In that situation, one is like this, x1 prime, x2 prime, and x3 prime, and another is like that. This is x1, this is x2, this is x3, right?
Yeah.
Let's assume they are actually separated infinitesimally. What do we mean by infinitesimally? That means we just need a small rotation to go from one to another. That means this angle, this is basically differential angle, some d omega. So we can view this thing as like this. The first one and the second one actually separated by a rotation along some axis in hat. In hat, I should write. In hat is the direction of axis. So if you are confused by this, then just draw 2-dimensional diagrams, then that will be easier. So in 2-dimensional diagram, like rotation axis is our z-axis, like that's pointing outward to the plane, and this is our x, this is our y, this is x prime, this is y prime. This is what I'm talking about. This angle is our like differential angle, d omega. Okay.
Yes, right. All right.
Okay, so in 2 dimension, like here, what happens? If we have a differential separation, then we have x prime y prime equals to cos d omega sine d omega, right? Minus sine d omega cos d omega, and then xy, and the z remains same, so we do not have to worry about that, right?
Yeah.
So we wrote this matrix earlier, so that's we are using here. So cosine d omega, when d omega is really small, how much is that? How much is cosine d omega?
1.
The first one is approximately 1, right?
Approximately.
So we can write it as like approximately, this is 1, and how much sine d omega?
This is also just d omega.
It's approximately just d omega. And this one negative d omega, and this again is 1.
Yeah.
So if we expand, our x prime is approximately how much? X plus y d omega, right?
Yeah.
And y prime is
Minus x d omega plus y.
x d omega, negative x d omega plus y, right?
Yeah.
So how much is the separation between those two? Like dy equals to y prime minus y, or dx equals to x prime minus x. How much is that?
Can you repeat?
How much is this dx? Infinitesimal change in
Okay.
x.
Okay, it's y times y times d omega.
Y times d omega, right? Oops, I wrote a lower bar. Okay, d omega, and then dy is negative
minus x d omega.
d omega. Okay, that's something interesting. So we have basically written dr equals to something linear in omega and r. Can you suggest me some relation that r and omega should have in between?
Well, we can write it dx plus I plus dy plus j, and then we can replace it by the
Can
direction.
we write like this: d omega z hat cross r vector? Can we write that?
Yeah. Yeah, we can.
Yeah.
Okay, great. So in 3 dimension, in a more general setting, when we have an arbitrary direction of n, we can actually this is the direction of our rotation, right? Z hat was the direction of rotation, right? Like way it was rotating. So we call it as d omega vector cross r. So we generalize this idea into full 3 dimension. So you can actually convince yourself as well by drawing diagrams like this. If you have a particle moving on a circle, and your coordinate systems is origin has this point, and this is your
cross r type thing, I think. If
Yes.
we differentiate this with test photo time.
Yeah,
No, exactly not that. But
dr equals to infinitesimal change in angle cross r. We can convince ourselves like really easily. Okay, this is going to be interesting result because so if this infinitesimal change takes time dt, then we can say that dr over dt is basically the velocity of that particle seen from which coordinate? With this frozen coordinate, that means static one, equals to omega cross r, right? Where r and v both are measured from
yeah.
Okay, so now it was moving on a circle. That's why we got this kind of thing. Like if we consider some particle, like here we consider just two arbitrary two arbitrary coordinate. One is rotating, another is not. Now both of them are observing some point particle p, and that p is also moving, and the rotating coordinate system that observe a velocity of dr over dt, or just v rotating. V rotating is the velocity observed by the rotating coordinate. Then what will happen by vector addition? Then due to only rotation, we already had v equals to omega cross r. Then we fixed the total velocity seen by the fixed observer would be v plus v rot, right?
Yeah.
Do you get that, what I'm saying? So that particle has its own movement, it has its own velocity. So the rotating coordinate, if rotating observer, if it sees as is static, then it's actually rotating in the frozen coordinate, like static coordinate, right? And that's relation is this
relative velocity type thing.
But if that thing is already moving in this rotating coordinate with some velocity v rot, then we have to add velocity, right? Like we have added velocity v dot in both sides. Like v fixed c is, this part is for the coordinate rotation and this part is the velocity of that particle seen as in rotating coordinate system, right?
Yeah.
So we generalize the idea as dr over dt in fixed coordinate, fixed means inertial coordinate, equals to dr over dt seen by whom? Seen by rotating coordinate.
Rotating coordinate.
Plus omega cross r, right? When their origin is same, they are just observing same thing. So this r is actually seen by whom? Fixed or rotating one?
Which one?
This r.
These are remember the fixed one. From the fixed one.
This for fixed one. Actually, we need to separate a little bit. Why? Because there are two kind of motion here, right? There are two parts of that same motion. So we need to be a little bit more careful about this. Look, they have their like their what I can say, they're already rotating with respect to each other, right?
Yeah.
So when they see a point which is, say, static at one frame, that means probably its v fixed is like fixed.
Yeah.
If v fixed is fixed, then this thing has to be a fixed vector. R has to be a fixed vector. So in that case, like this thing is 0, so dr over dt rod is equals to negative omega cross r fixed. You see that? I mean, in frozen coordinate, this particle has a velocity dr over dt fixed equals to 0. In that situation, what happens? This thing has to balance, right?
Yeah.
So dr over dt rod equals to negative of omega cross r fixed. So remember this thing, otherwise we might get confused. So this is what happening. So this part is coming from purely rotation, and another part is actually adding something. When this is totally fixed, then dr over dt is seen by the moving observer only, like rotating observer, and due to its own rotation. So for any vector that transforms like r, we should have the same transformation rule. So for any vector a, dA over dt seen by the fixed observer is equals to dA over dt seen by the rotating observer plus omega cross a, right?
Yeah.
Can you repeat that, please? I missed that part.
So you had your r vector. So your r vector, when say r vector was here, so when you rotate a coordinate system, r vector becomes at this point due to its your coordinate rotation. So now, say if you had any other vector over there, like the same r vector is actually it's represented by an electric field vector. So when you rotate the thing, electric field vector should change it accordingly, the similar manner that r does, right?
Yeah, I got that.
So that's why it's general for any vector. Okay, now we are almost done. So we can do our derivative of that dr prime over dt that we had written earlier, fixed. That can be written as dr over dt fixed plus dr over dt fixed. Agree with that? We just substituted r prime equals to r bigger plus smaller from the translation of two coordinates. You remember?
Omega cross.
No. You already like this is the operation.
Okay.
This is the operation ddt on fixed coordinate. This is the operation we have applied on both sides of this relation. We are generalizing everything.
Okay.
So we got that. On both sides, it become derivative with respect to fixed. So what is this thing? dr prime over dt fixed. What is this thing? It is basically VF, right? Like the velocity seen by the fixed observer, like the frozen observer, V fixed. Because r prime was the coordinate seen by the frozen observer, non-moving observer, and r is the coordinate of seen by the rotating observer or translating observer. Hello.
Yeah.
Yeah.
So now dr over dt fixed, what is that? We call it big V. V origin. It is the origin of oops, T, not T. It is the origin of the moving frame with respect to the non-moving frame, right?
Yeah.
Hello. Now we are reduced down to this part,
Yes.
dr over dt fixed. So dr over dt fixed, we can write it as dr over dt rotating plus omega cross r.
Yeah.
Okay. Now actually we can write it as like this, v fixed, like velocity seen by the fixed observer is separation between the velocity of the origin, like separation velocity of the origin plus velocity seen by the rotating observer plus omega cross r. Now
Yes.
apply ddt fixed on both sides again. Apply ddt fixed on both sides again. So if we apply that thing, v fixed, if we take derivative with respect to we take ddt. Okay, let me clarify this thing. How do I write? I write this way. ddt fixed on V fixed. Are you cool with this notation? Like, do you get what I'm saying? Are you okay with this notation?
Yeah.
Yeah.
This is the derivative seen by the fixed observer, basically. So I do the same thing all along. Big V origin plus ddt fixed V rotating plus ddt fixed omega cross r. Okay.
Yeah.
So what is ddt fixed on V fixed? What is this term?
The acceleration fixed.
Acceleration of what? You said A fixed, right? Like that means the acceleration observed by the
fixed frame.
observer. Yeah,
Observer.
fixed frame. Yeah, non-moving observer, like inertial observer, right? Then what is this term? V origin, ddt fixed V origin. What's that?
Acceleration of origin with respect to fixed frame.
Yes, acceleration of origin, right? So we call it big A with respect to fixed frame, and we do not need this thing in terms of rotating frame, so we do not bother about saying fixed or rotating. Okay. Plus, now ddt fixed on V rotating. This is totally meaningless. We need to reduce down this thing into rotating derivatives. So remember the identity we derived earlier. So this is ddt rot on V rot plus omega cross V rot, right?
Yes.
Plus ddt rot on omega cross r plus ddt, sorry, not ddt, omega cross r. Do you agree with that?
Yeah.
Yeah.
Can I take 10 more minutes today? I'm sorry.
Yeah, sure.
Now, though. I'm almost done here. So, A fixed, acceleration observed by the fixed coordinate, fixed observer, is equals to acceleration of the origin of the moving frame with respect to the fixed observer plus ddt rot on V rot. What is that?
Velocity with respect to
rotating observer.
No. This is not velocity. Derivative of velocity. This is.
Yes, acceleration with respect to rotating frame.
Yeah, we call it just A. We are going to drop all the rot index here because we need not anymore. So it's defined like ddt rot V rot is A. Okay, plus omega cross V, just V is just V dot, plus ddt dot on omega cross r. What's that? This is omega dot cross r plus omega cross ddt rot on r is just V or V dot, whatever, right?
Yeah.
Remember, I did not have any just V. I'm just writing V equals to V dot. I'm dropping the rot sign over there. I need not to write it anymore. I'm done with my calculation. I did not have any V earlier. I always had V dot or V fixed. I can drop one of those, right? I'm dropping the rot one. Okay, so plus omega cross R. Do we have any repeated terms?
Yeah, omega cross V.
So I, instead of A fixed, I just call it AF. Then A origin, I just call it big A plus small a plus these two terms add up. So omega V twice V omega cross V. Then plus omega dot cross R plus omega cross R. So by Newton's law, this AF acceleration seen by the fixed observer, non-moving observer, is basically applied force divided by mass, right? Or basically by Newton's law, this is F equals to MAF. Now I can substitute. I can substitute this thing and get M small a plus M big A plus twice M. Actually, I should write the other one first, I believe. No, let it be. Let it be like this. M omega cross R. Then plus twice M omega cross V plus M omega dot cross R. What is omega dot, by the way?
Angular acceleration.
Angular acceleration seen by who?
Rotating.
Seen by the rotating observer. Actually, these are the same. I did not prove that. Okay, let it be just single dot. Okay, now I need my MA. Like I want to see the form of Newton's law in non-inertial frame, not the inertial one. I'm not interested in the inertial frame. I'm interested in the non-inertial frame. So I'm interested in MA, in small a. So if I rearrange, I get MA equals to big F, the true force, minus M small a plus minus M omega cross R minus twice M omega cross V minus M omega dot cross R. Where all those R and V, those are actually seen by the rotating observer, not the static one. So we can call it as an effective force, right? Interpreting this term as force terms.
Yeah.
So look, we have recovered our F equal MA form, but we had to like tweak our definition of force, right? So F equal MA is again recovered, but our definition of force is now a little bit changed. So we have to add some extra terms.
Fictitious forces.
These are fictitious forces, right? So they have names. This is inertial force. Okay, what is this? Do you know what is this? Inertial force has a definition: F inner is negative ma. And then this one, you know what's this? No, it's not Coriolis. It's centrifugal force.
Oh, yes.
So it's centrifugal force.
Yes.
This is negative m omega cross r, right? What about this one? This is your Coriolis force. So if Coriolis, this is negative 2m omega cross v, right? And then you have your final term. We call it angular inertial term. Inertial force. F ang. This is negative m omega dot cross r. Okay, so these are our fictitious force when we have a non-inertial frame. So in any non-inertial frame, like at max, you can have these four kind of forces. So question is, what is the common feature do you observe in these four kind of forces, four non-inertial forces? At the first, no, what is the common feature between those?
Cross product.
I think senior people can actually tell us better. So Pooja Bajaj or Dr. Friedberg. So what are the common feature do you see in these four forces?
Not clear.
You cannot see it?
No.
Is it because the handwriting?
No, it's my brain.
Oh, so you cannot see any like common feature between those. That's what you mean?
Yes, that's what I mean.
Okay. Yeah, okay. Then Pooja Bajaj. Do you see any common?
Well, except the inertial force, the rest of the forces are omega dependent.
Okay. That's a different thing. But all of the inertial force, all of the forces, like fictitious forces, they have a common feature.
Fictitious forces.
Well, they have a negative sign in front of it. Is that what you're talking about?
We could always absorb those negative signs. There is a thing that cannot be absorbed. That is the mass term. All of those are proportional to mass, right?
But isn't that unnatural? Since we are trying to write like F is equal to m type thing. So
no. Look, we are comparing with the force, like real force with the fictitious force. This force, like probably the object you are looking at is probably has an electric charge Q and moving under an electric field E. So that force might be F equals to QE, and that doesn't necessarily has M inside of it. It might not be proportional to M.
Yes,
but all the fictitious force have this one common feature, that they are proportional to mass, and that's a really important thing here. Do you know any force that is proportional to mass? Do you know any force that is proportional to mass?
Which is proportional or not proportional?
Which is proportional. I already gave an example of
gravity.
Exactly, gravity. Gravity is the only force known to man that is proportional to mass. And now we have discovered that in non-inertial frames, the pseudo forces, that fictitious forces, those are all proportional to mass. That means there might be a chance that we can interpret our gravity as a fictitious force as well.
Yeah.
Might be. That's the point we are trying to explore. Interesting, isn't it?
Yeah.
Yes, that's nice.
Wow.
Okay. Did you like today's class or not? I think it was a boring mathematics.
I had to go, so I have missed the last part actually, the derivation of the last equation. So can you?
So you can find it in books.
Okay. Goldstein.
Yeah, Goldstein.
Okay.
You can find it in Taylor. You can find it in Thornton Marion.
Okay.
Those are standard derivations. So any comments about today's class? I think I was a little bit late. I'm really sorry. Like I'm already still running late. Like I'm lagging behind. I'll try to catch up next week. I'm not sure. Every year this happens.
Actually, I have a